Let's take a few minutes and look at the difference between disjoint or mutually exclusive events and independent events. From here on out, I'm going to refer to mutually exclusive just to simplify things as disjoint events. So first of all, let's start with the general addition rule. So the probability of A or B is simply the probability that A happens plus the probability that B happens minus the probability that both of them happen simultaneously. It's important to subtract off the and probability so that we essentially don't double count outcomes that happen both within A and within B. So let's assume then that A and B are disjoint. Here's a picture of what that looks like. So in terms of a Venn diagram, here are all of the outcomes that are possible when A occurs. Here are all of the outcomes that are possible when B occurs, and they don't share any outcomes. So in other words, they are mutually exclusive or they are disjoint. They can't happen simultaneously. So what that means is if I want the probability of A or B, that means that I can take the probability of A, I can add it to the probability of B, but then notice there isn't any possibility that there are events in A, outcomes within A that are also within B. They are disjoint or mutually exclusive of one another. So the probability of A and B is 0. There's essentially no possibility for double counting. So when I add the probabilities of A and B, there's nothing that I have to subtract away. So the key here is that disjoint implies that the probability of A and B is in fact 0. So now let's take a look at, in this situation, can the events A and B, can they be independent? Well, let's start with the definition of independence. So to be independent, the probability of A, given that B has already happened, is simply the probability of A. So in other words, A and B are independent. Whether B happens or not, the probability of A is the same. It's simply just the probability of A. So let's assume also that the events A and B have non-zero probabilities, and let's rethink what the expression here, the probability of A given B, looks like. Let's look at that in terms of the conditional probability formula. So the probability of A given that B has happened, that's the probability of A and B divided by the probability of B. But starting with events that are disjoint, I already know something about the numerator. I know that the probability of A and B is 0. So when I divide by the probability of B, the conditional probability formula gives me a probability of 0. So understand, this means that 0 is the probability of A given B. Well, to be independent, the probability of A given B is supposed to be equal to the probability of A. But that's impossible because I know that A is a non-zero probability. This expression can't end up being the probability of A because the probability of A given B ends up being 0. I know that can't be the probability of A because I can see in the Venn diagram that there are outcomes that result in the event A occurring. So ultimately then, if we start in this picture with a Venn diagram with events that are disjoint, I know that they aren't independent. They aren't independent because the probability of A, given that B has happened, isn't equal to the probability of A. It equals 0. And the probability of A isn't 0. Another way to think about this then, you can actually think about events that are disjoint. You can think of them as being completely dependent upon one another. So let's consider the probability of A given B. What this means is that we know that B has already happened. Well, if B has already happened, the outcome is within the B circle. But what that tells me is that I know for sure that A can't happen because there are no outcomes in the A circle that overlap the B circle. Knowing that B has happened, A cannot happen. Similarly, if I know that A has happened because these events are disjoint, I know that it's impossible for B to happen. So I know they're completely dependent upon each other. Knowing given information about one event tells me whether or not the other event can happen. So given that one event has happened, it is certain that the other event can't happen since these are disjoint events. There's another way to consider this. So we've already explained if events are disjoint, like we saw in the previous Venn diagram, then they can't be independent. Another way to think about this is to explore the contrapositive of this if-then statement. So another way to write this, a logically equivalent way to write this, is to switch the hypothesis and the conclusion and then negate them. So we're going to start with this. Instead of they are not independent, we're going to negate that and start with if the events are independent, then we'll negate this and we will look at the conclusion that they are not disjoint. So in other words, we've already explained if events are disjoint, they're not independent. Another way to say the same thing is to start with saying if they are independent, then they're not disjoint. So we can explore this just by looking at the probability formulas that we already know. So again, we need to assume that A and B, those are events that have non-zero probabilities. And this time we're going to look at the general multiplication formula. So in any situation, the probability of A and B, I know that that's simply the probability of A times the probability of B, given that A has already happened. That's the general multiplication formula. So if I know that two events, A and B, though, are independent, the general multiplication formula now looks like this. The probability of A and B is simply the probability of A times the probability of B. And the reason I know that independence accomplishes that is because of this expression. If A and B are independent, the probability of B is not dependent upon whether A happens or not. So given that A has happened, that has no effect on the probability of B. So the given A, this condition here, is not necessary. The probability of B given A is simply the probability of B, just by independence. And that gives me this special case for finding the probability of A and B. So now what's important here, if A and B are both non-zero probabilities, as we stated above, look at this. Now I know that the probability of A and B, because both the probability of A and the probability of B, because neither one of those is zero, they're both non-zero. When I multiply those together, I get a value that's greater than zero. So this probability, the probability of A and B, has to be greater than zero. What that means is that the events A and B can happen simultaneously. The probability of A and B is telling me the likelihood of A and B happening at the same time. So notice what we've got then by starting with events that are independent, right here. Starting with events that are independent, I know they're not disjoint because I can see here this probability is greater than zero. That means that the events A and B can happen at the same time. If they can happen, then they can't be disjoint. Starting with independent events, I know they're not disjoint. That's another way to consider what we considered on the previous slide. That was if events are disjoint, then they are not independent. Two ways of looking at the exact same relationship.